As I sat in the waiting lobby for my eye doctor appointment, I thought to myself, how do people in third world countries get their nearsightedness prescribed without trained professionals? Then it occurred to me, there had to have been a better way. I got with a couple of my buddies.
Okay.
I'm Nikhil.
I'm Saahil.
And I'm Avi.
And
this is Eagle Eye.
1 billion people in the world suffer from unaddressed vision problems. We developed Eagle Eye using Python and OpenCV2 to help developing countries easily and efficiently prescribe lens powers to help world leaders supply glasses to the masses. Our program has 3 simple steps: calibration, user distancing, and blur adjustment. Calibration only has to be done once, and this is to allow our program to run on any phone with any camera on any object. To do this, the user takes a still video of a known object from a known distance. For distancing, the app accurately tells the user where to move for the diagnosis. Then, the user will adjust the blur values on the phone screen so it matches what they see in real life.
First, the user inputs a video of them just holding their camera still in front of an object. And we calculate the focal length of that camera using this formula. Then we use the focal length found from that formula to estimate distances to objects in the future. So when the user wants to find out how far he is from the object, we'll find a bounding box for our image to approximate how wide it is in pixels, and then use our focal length to find how far the person is actually from the object. How we do that is we find what's called gradients using edge detection. Now, gradients are basically just the greatest contrast in pixels in any image. And we use specifically canny edge detection, which is a 5-step process outlined up here. Using that process, we will find the greatest gradients in any frame, and then those greatest gradients will be used to create a bounding box. So now that we have the bounding box and our focal length of the camera, we can see how far a user is from their actual object.
When we're trying to calibrate our focal length for our camera, we input a video, then we calculate the bounding box around the object for each frame. Then using the initial distance that you know that you are from the object, and using the approximate width of the object, we can use the formula that Avyukth mentioned earlier to calculate the focal length. Now we can run this through every frame of our calibration image and then average those out and then get our true focal length for our camera, which we'll be using for the rest of the procedure. Once we get the user to stand a specific distance away from the object, we blur that object on a different image and then mask it over so that only the area within the bounding box is blurred. At this point, we have 2 threads running, one that displays the video and one that reads in the blur values from the input. This way, when the user changes the blur amounts, it'll show it live on the actual video and blur the inside of the bounding box by a different amount. The user can tweak the level of the blur in the blur map until it matches what they see in real life. Now that we have a level of blur that is most similar to the patient's vision, we need to convert this level to an actual eye power. Now we calculated this using the Snellen eye chart. We created a regression for this level of blur to this eye power by blurring the image until we could only read up until a certain line. Once they have a good match, it displays what the actual vision power is.